second presenter of the session, who is Patrick van Hees, who is a professor at the Department of Fire Safety Engineering and Safety Systems of Lund University in Sweden, and also was recently elected as chairman of the International Association of Fire Safety Sciences, so is also here to represent IAFSS. Patrick is not, alas, an Edinburgh graduate, but does work with us. We have a joint international Masters in Fire Safety Engineering program, which we call the IMFSE. Many of the students from the IMFSE are here today. And Patrick and his colleagues at Lund University work with us as part of that program. So that's one of the reasons we wanted to make sure that we gave an opportunity for Patrick to speak. I should also say that all of the talks that are being given here, the only thing that we asked the speakers to do was within some general sub-discipline of fire safety engineering or some realm of relevance to deal with the where are we, how did we get here, and where are we going question in their own way, aside from the medal lectures, I should say. And in the case of Lund University, I basically said to him, risk, I think was the word I used. So we'll see what Patrick does. Yes. These mics are on. There you go. Yep.
Thank you, Luke. I will use the word risk, to be honest, but I will talk a lot about performance-based design, which is not equal to risk, but it's a part of it. And I first of all, of course, want to thank the organizers for inviting me. And Luke gave already the link through the education into our international Erasmus Mundus master program, and I'm also very happy to see a lot of the students who have been in the program and been also in Lund here today. So it also makes me a bit emotional, but I will keep that also for the dinner. But it's nice, and also nice to hear that one of the students managed to ask a question to John, that John became a little bit speechless. So thank you. So about my speech, I will talk a bit about trends in fire safety engineering, and I don't have all the nice and big pictures which we saw in the previous presentation, but I picked a few of them also in it. And as I said, I am more from a background. I started in reaction to fire, and then I moved a bit immediately in fire resistance testing when I was in Ghent as junior researcher. I had to do all these fire resistance tests, and then I moved on back to reaction to fire and full scale testing at the SP in Sweden, and then they needed somebody who wanted to start their modeling group, so I started with that, and I thought now it's maybe good to go to the university and try to capture that everything. And then I came to Lund, and Lund is of course also known about their risk performance-based designing and human behavior and so on, so I tend to keep that also inside my talks, but it's not so easy because you have to cover so much these days in fire safety engineering. But in order not to talk for an hour and only for maybe half an hour, hopefully, I keep a bit on the fire development in a general way, and I talk a bit first about the process and explaining a bit how it works, at least how it seems to work in Sweden these days, because we have a performance-based design regulation. But I'm gonna double up a bit what we heard before on materials and new areas, on the modeling and also on the energy conservation. And I wrap that up then with giving a lot of challenges, which are mainly questions for you. I'm not going to answer them all, because otherwise we can't do research. Fire safety engineering is... The word fire safety engineering is sometimes used in different ways in different countries, to be honest, I've noticed. But when we talk about a lot about fire safety engineering in Sweden, we link it quite quickly to performance-based design. Of course, it's not only that, but that's why I want to talk a bit more about that. And we get that not only in buildings, but it's getting into other areas like marine applications, ships and so on, and even trains these days you're allowed. So you're allowed to do a performance-based design of a ship, starting to use other materials than steel. And steel, of course, is, for instance, in a ship very nice to use because it stays quite in place, at least when something starts to burn. If that would be some composite and it starts to burn and make a hole, then you can imagine what happens with the ship. And we design our evacuation of our ships, and I had a nice master thesis presentation yesterday on the evacuation to try to get the people out of the deck onto the rescue areas in the ship. But then they maybe have to get out of the ship also because there will be holes and it will sink. So we need to think about this performance-based design in a whole system in that case. The other thing is that we have more and more new materials coming up, and we need to know how we can deal with the fire behavior, and that can be just from very exotic new cables on this picture to in fact technical textiles which are used as a building envelope, and then you know what's happening if there are holes and so on, is that beneficial or not, and so on. This is something which I can go a little bit quicker because I would guess most of you know that, but there's the difference between prescriptive and performance-based. Prescriptive, you have the clear criteria, and I use a bit the European system. I've been unfortunately a bit also responsible for these Euro classes when I was project leader at SP in the development of the SPI, so don't throw the stones to me afterwards, but some of the things came through a lot of research, and then it came into the political field, of course. And you have the rules there with the Euro class B, which you can use for instance, evacuation routes. You can have specific fire resistance tests and specific widths of doors and so on. And that's the, let's say, prescriptive side. The other thing is the performance-based design, where you start from an objective and that you have to get these people out before there is any harm. And we know that. And this, of course, have introduced a lot of more flexible solutions, bigger areas and so on. And I think we have seen a number of these examples of buildings previously, and this is just a sports arena also with these, again, technical textiles. Also led to possibilities for cost efficiency, as was pointed out earlier. And the general approach, I try to condense this large flow chart from SFPA into a few steps, but you start with scope, goals, objectives, go to performance criteria, design fire scenarios, run trial designs and so on, check with these performance criteria, and then do a choice of the design. There's some loops in this system, but I didn't want to make it more complicated for the presentation. But you all know this type of procedure, and it's not only in SFPA, it's also there are a number of documents in ISO. When we do this trial design, I give a simple example for evacuation, which is one of these kind of objectives or also criteria we use, and I use the deterministic, I don't use the risk or the probabilistic design, but this is a bit easier to go through. You take this fire scenario, you have a design fire, then you do calculations, smoke and fire spread, you use some CFD code or zone model. It's up to the user to do that, and then you do also link that with evacuation modeling. And we get into a system where these things are getting coupled, so you get more flexibilities. And then you see if the things are working out well or not. How do we do these design fire scenarios then? This is, and I'll go a little bit quick here. You can't do all the different types of possible scenarios everywhere where there would be a kind of a ignition source and start the fire. You can do that in a probabilistic way, but the work anyhow becomes quite complicated, so you have to go through a number of sets of scenarios, and mainly, of course, those who threat a lot the building, if we look now to building. And you have to look to the state of the art of the building, and maybe even look a little bit further if we know there are other applications for that. And all these things, and I'm not going through them one by one, but it goes by defining what components there are, what the building characteristics are, and so on. And then you can do a lot of risk analysis, and you have a massive amount of tools for that to do, where you look to the failures and the effect of that. You can do what-if analysis, you can look to the historical data, and so on. We always have to think about, when we use these techniques, we've applied to one building, And here comes my first question already. Can we just do that for other buildings? Can we just use, for example, and I exaggerate a little bit because I want to create a little bit of reaction, can we use the data statistics, for instance, for sprinkler activation times, which you have in buildings from a certain source in the US? Can you suddenly use that on a ship? Maybe, it's quite easy to answer that one, but we might do that from time to time. And this probabilistic approach then goes into statistics on fire frequencies, initiation frequencies, hazard, and so on, and how reliable it is. And as an opposite of maybe probabilistic, you go on this deterministic approach. So you use some calculation methods, and also there you need test data maybe or background data for these scenarios. And quite often we use somehow a mixture. We go through a risk analysis and define a number of scenarios, do that maybe with some kind of a statistic and probabilistic approach, and then we get the scenarios and we do a kind of deterministic approach where you do the calculations of the fire and smoke flow. But it's important to know that this hybrid solution is working really. And of course that will then, this fire design scenario analysis leads to a design curve which has all these characteristics of who's there and also how the building looks like in it. And here we come to one of these fantastic graphs which is used, at least in Sweden, or quite often used, the so-called example of the design fire. We can discuss a lot on the numbers. But this is one of them, a growing phase, a steady state phase, and then a linear decay. But there are others, of course. This is not the only one, but there's an example. How do we get that then? Because we use it, but we have to try to get it also. And maybe the first thing is it defined maybe by the regulator soon? And we see this trend, to be honest, in Sweden, where the regulator has said this design fire should be at least something like this. And they start to saying it. And if you say also, even and if you use a CFD model, then you have to use this type of, let's say, characteristics for the fuel, because you should not try playing with these numbers. But quite often, at least in a lot of cases, we do maybe use real skill data, combination of both building content and building products, and then we use modeling, where you maybe link these a small scale test to a large scale test, or we maybe use advanced flame spread models or pyrolysis models. And of course you can use still a probabilistic also, where you just use probabilistic approaches and do maybe, for instance, a whole range of different numbers of design fires, and you tend to get maybe an average alpha value with a certain distribution and so on. Or you just use the word which sometimes is set some magic numbers. And there are some articles on that, especially when it is related to design fires. Quickly going through how you can get this data. Now I come to my background as doing a lot of fire development tests and full-scale tests. You can, of course, start doing full-scale tests. For a room scenario, you can put everything in place and you can run it. Those who do tests, that's quite often done. And it's maybe done more than you think, at least in Sweden, where if the fire consultancy doesn't really know exactly how it would be, that there will be kind of a small setup, at least to know the growth phase in it. But of course it's not possible for all, because it's costly, so you cannot do that. So you can maybe rely on the data which is available. You can test also an item of furniture, or whether it is, in my time from SP, we tested a lot of these different items which were maybe in rooms, even replicates of art, to see how, if this plastic art piece started to burn, how would be the heat release. And then you can link the small scale test, and I use now the calorimeter, but of course the FPA apparatus is another alternative. I don't want to say that it's only the calorimeter, but you can do this link. You have a small scale test and you link it then to a larger scale scenario and get some fire development which you can use then for instance, this alpha t square value. You can do it more complex. That means you can put this everything, and this is an example of a cable, 3 cable trays, in a kind of a electrical appliance setup, you can do really the flame spread modeling within the CFD. And I don't use the animation, but you can then predict, let's say, the fire spread and get that heat release as an input for all the other calculations inside your setup. What are test methods? And I use then the cone calorimeter as an example, but you have 10 by 10 samples in that. And then you try to extrapolate that. And is that then something which, in fact, something where we can work with? We see examples of simple particle boards, so some paper wall linings and so on, and that works rather well. But if we do that and we try to use that inside this so-called performance-based design, we have to consider a number of things here. And I know there will be talks about, let's say, material modeling and so on, and let's see how these two matches with each other. You have to see if these models are really validated. Are they applicable for your products you're going to use? At what scale they've been used? Are the materials you've tested really used in the same way? That means in the same realistic way. Mounting, for instance, now they are set up on the building. And can you get the input data? Because many of the studies, and we increase in this level, and it's nice to see this progress, but they still use it with traditional known materials. If we're very advanced, complex, do we get the input data? And this is one of the projects I at the moment have in Sweden together with DBI in Denmark called Fire Tools, where we're going to look more and more how to get that type of data for general purpose materials and trying to model that at the whole level. And this is just an example. On the left we have again this simple, let's say, particle boards 10 by 10 or some paper wall covering on it. To the right we have a complex sandwich panel. So you don't get that into 10 by 10. So you have to do something about that. And you cannot test this steel, cover it completely and with a combustible material inside it so that nothing can escape and then say, look, it didn't ignite. Yes, it didn't ignite, but and you use that then in your final assessment for your and you know I exaggerate a little bit, but we have a number of examples for that, unfortunately. I'm gliding a bit on this energy demand also, because that also is interesting. We get more and more demands on the thermal insulation. We have to use new materials in Sweden, and you could think about how is it possible Sweden is so big, but we concentrate also all the people to the big cities. So that means in Stockholm, the building area is very important. So by thick insulation on walls, you reduce the number of buildings you can put on the same area. And that means a cost. And you can maybe say, why isn't that exaggerated? You have so much space there with all the forest. But no, the people want to be in the big cities. And that means the designs have to work towards trying to get these thinner walls. And maybe you have to go then to other solutions. And you have new materials, but how do they behave? Another thing we have seen, and there are a number of real-scale cases or real fires in Sweden about that, is we get other type of ventilation. A lot of reduced natural ventilation. We tighten the windows and so on. We have other type of window system, glass systems and so on. And we tend, and we have seen a number of examples where you might have an underventilated fire. Maybe just, I think there was an example of a fire started in a bedroom where only the sofa in the bedroom burned. And there was not much more than a fire, but 4 or 5 people, I think it was 4 people were killed in that fire because there were other conditions suddenly. And do we get there with our models? And I think John de Ries explained a lot about these things on underventilated fires, but there's still a lot to learn, and we try to cover that by saying, okay, all our scenarios are quite often well ventilated. We know, as I said, a lot on room fires. And I know that from my origin at SP, where there's a lot of room fire tests done. We know a lot about the, let's say, wall linings, furnitures, and so on. But these days we see that the fire development quite often also spreads inside the construction. And we have to know about this, and we started the project on what we call construction fires. That means that the fire is spreading inside the construction and you don't maybe see where it is, or it suddenly comes out somewhere where you don't expect it. Do we then cover the fire scenario if we do traditional test? The SPI, which I said I was a bit also responsible for, is linked to a room scenario. It's not linked to the scenario to the right, which is a facade scenario. So you cannot use the test data and the classes just by extrapolating to facade fire. There are other thermal attacks in that. So we have to think about that. We have also to see how we test these things. They're complex system, and I've been shouting a bit sometime in the desert about sandwich panels and facades, that these things are systems. They are not a single material. There's a complete system where not only, let's say, the outside, or it's the whole system, what I say, which is very important, to be honest, not a single product, because it's the whole area. And this is an example of a facade fire in Korea, where you have not only maybe the materials plays a role, but also how the buildings are connected to each other in almost a chimney effect. We had a lot of problems, unfortunately, in Sweden with fire in schools and attics. The fire gets into the attic is one single compartment, starts to burn, it starts to collapse, and everything falls down, and the building is gone. And these fires are sometimes very difficult to see once it's in the attic, and once it comes out of the attic, it's a loss for the fire brigade. And they come on the place, and they just have to protect maybe some of the surroundings, and that's all. It's quite frustrating for them. So I come to a bit of the conclusions, where I put some, let's say, challenges. I think it's important when we do this performance-based design that we try to do some kind of harmonization between different areas, whether it's transport or building, that we don't glide away a bit. And I've seen that a bit, that is happening. We tend to build up our own test system for the prescriptive solution, which is then a very complex number of tests, depending on whether it's a train, a ship, or a building. In fact, if we look to performance-based design, we could try to do a good job and maybe start from the same set of tests and not trying to develop our own little world. But it's difficult because it's between different areas, sometimes different regulations also. It's important to give more guidance for performance-based design in a way that we don't lose the flexibility, because that's what's important in performance-based design, that we still keep this flexibility to build a bit in a general and with bright ideas on how to build a building, and that not suddenly the regulator starts to put prescriptive performance-based design, that you say you have to look to this, and this, and this. There should be guidance instead of maybe. And if we're not cautious, we go into a prescriptive performance-based design, what I call. It sounds a little bit maybe getting complicated and playing with words, but it's in fact something we have to think about. And you can see it maybe as a wave system, that you go from prescriptive to performance and so on. But it's up to us also to see that we establish these rules. And one of these rules, of course, is a quality control and how to do that. And I can only know the Swedish system, so but there's, in Sweden at least, work to do also there, because we had this type of performance-based design and using of magic numbers, design fires from 5 to 10 megawatt for a almost identical building, and that means that how is this put into a quality control? And that more maybe also administration stuff, but it's important. I think also personally that we have a lot of focus, and I don't want to say that everybody is that, but at least I see it at least in Sweden, that we have put a lot of focus on what we call safety of life, focus on the functional performance. We've looked less to maybe the construction, if it's not connected to safety of life, of course. But let's say the property loss has been a bit on the second part. And that's mainly because the building regulations in Sweden, they, in fact, of the Ministry of Housing, are focusing on safety of life. So the example I gave with the school fires, we have not one single person have been killed in a school fire in Sweden over the last 15 years. But on the other hand, so the building regulation on that part seems to work, between brackets. But on the other hand, if we look to the costs, we are up, and we got it a little bit lower because of research now. But the cost for school fires in Sweden were, and now I have to calculate, but without doing an error, it's about 100 million pounds a year, was it? But that was not really the major problem for the Ministry of Housing. That's more towards the insurance business, and maybe because it's not part of it. So, and I think that's one thing where we have to think about to general view, and that means that you have to start in the beginning in your process of performance-based design to consolidate this in your goals and objectives if you want to have more than just fulfilling, let's say, the regulations for housing. And the same is linked to what I call then the continuation of operation, which is not only the loss of maybe the real, how should I say, the building, but the running of the facility. And that's maybe for buildings, if we think about residential buildings, maybe not the highest priority, but if we look to industrial application, and for instance, or electrical power plants, that's a whole different thing. And it's no secret of that. There are articles about that, so I don't say something outside of the confidential area. But there's been 2 years, or I think it's almost 3 years ago now, in Sweden, a vacuum cleaner who burned in the reactor zone of one of our nuclear power plants. That fire took place for 1 or 2 hours. They didn't really know what was happening inside because it was in the containment. They just saw the temperature rising, and then they saw luckily it was going down also, because they couldn't enter the building because they were doing pressure tests on the container. This vacuum cleaner, well, you can think that the design fire or the high heat release is not high, but it produced a lot of soot. And due to the fact that it was in the containment, they couldn't take the risk to say, okay, all the electronics, all the things which are in this containment, they are still working, but still working for how long? So they did a lot of replacement just by not knowing the information about how these components reacted after a fire or during a fire. So, and that means the plant was stopped for more than 1 year and a half. Cost 100 million at least for the production cost, and that's a big number. And that's maybe also valid for the functional performance of safety systems. How well do we know that our safety systems, like, for instance, to change ventilation systems, and in case of a fire, how well they work? We all know the Mont Blanc fire, which was a long time ago, but they tried to change the ventilation once the fire started, but all the cables were burned, so there was nothing to do anymore. And trying to send somebody in there, and that's not so easy. So we need also the appropriate tests to cover all these scenarios if we want to base ourselves on tests, of course. I'm not going to say that you have to base everything on tests, but to know these design fires. We need, if we talk about risk and probabilities, we need good statistics and know how to use them. I think both the UK and also Sweden, and I think the US also, have good statistics, but that's not everywhere. We don't get out everything always out of it for our design. We have to also get this feedback loop from real accidents, case studies, learn from what's going wrong. And maybe even, and that's maybe sometimes the most difficult thing, is learning what did work. And that's something which is disappearing. We have to develop procedures to obtain this reaction to fire or fire resistance to other exposures, and now we come into the modeling. And it's important to do this link between risk analysis and, for instance, design fires. Sometimes these two are just lost because we just use the numbers from the previous. We don't do back a risk analysis the step before. The submodels, we need also the input data. It's not only, and that's one of my so-called arrogant expressions that I use, we're not only working with PMMA and particle boards. We have a lot of other things in a building and complex systems. And if we use the models, we have to verify and validate them. It's a big task for the CFD model people to do this work. We know that there's a lot of work being done, and that's very positive and very good. But we have, every time we use the model, we have to say, has it really been done a proper validation for that what I'm using. And that's sometimes something we do not know. And that's important to know the uncertainties, because the uncertainties we have to know, all the ones in the process. From the beginning, when we design the scenarios, there are uncertainties. We have the CFD modeling, we have the human behavior, and somebody will talk about that later, so I didn't want to tackle that, because we need to have safety margins and minimum safety levels. And I was so happy yesterday I didn't have followed one of the master thesis subjects of our international students, but one of the students, he did interviews with the consultancies in Sweden and asked for what do you do on safety margins and minimum safety levels, and the answers were a little bit, to be honest, where we as educators have to think about. And then I come in fact to the educational challenges. We have on one hand to have the deep knowledge so that the people know what is the process of fires, and the other they have to train also. And then there I think we have a thing that our educational system is not always easy to do, but I know Jose will talk also about that tomorrow. And this list was long, but maybe not complete, I'm sure. And I think this is the message a bit because I took over IFSS, and I also have the pleasure to be the chair for ISO TC 92. I think this has to be done at an international level. I think it's not possible for instance, for a country like Sweden to establish that with 10 million. So we have to work international, and that's why I think it's so good that we have these organizations to work on that, and also the international programs for education. It's through synergy we get also further from different countries. And it's so nice to see that these Erasmus Mundus students from the joint program, they come from different countries, they come to the place, and I've noticed today, talked with some of them, not many come back to their own country, they don't stay maybe in Sweden, or some of them do, or in the UK, but they go to other countries like France and Germany and Switzerland. And that's nice to see. Because one of the things why I want to conclude with a little bit of joke, maybe some of you have seen it already, when we do a design, and this is just for a bridge design, you can have this kind of design criteria that say if I'm jumping on it, it should sustain my jumping, so it should not collapse. And that could be our design fire, which we have chosen. But then, of course, the next step is that if we put there a complete army or a high load on it, will it be enough with this jumping? And that can be also related to fire. I didn't want to give this example. It's always easier to go in another structural area or another area to think about that and not criticize ourselves, but think about that. The difference is, what I always say, is that in case of these structures, if this happens, if the design was not well done or the calculations were well done, the first time there's a truck going over that, you will see it. We maybe have the luck, to be honest, that we only will see it once it burns. And that's something where we have a difference, I guess. So, Luke didn't jump up, but he did like that 2 minutes, I think 5 minutes ago. So I will stop by saying tack så mycket. Thank you very much. You find more information on the department here, and on the right is maybe only one of the few high-rise buildings in Sweden. Okay.
Thank you, Patrick. We have time for one very important question, if anyone has, or even an unimportant question. Sometimes awkward.
Yeah, I think what you've been saying there, Patrick, reflects a lot on what we're doing in the UK and the problems we're having in the UK. But you did, sorry. Yeah, a lot of what you said sort of echoes here, but you did use the magic word quality at one point. And I mean, we've had cases, I'd like to say, in the past where the fire engineer that's designed their building worked out what the largest size fire they could cope with in that building, and then made that the design fire, which we always felt a bit bothersome. But we do have issues to do with whether the building that's actually built looks like a building that the fire engineer designed, and we get issues, to name a few, for example, of hidden voids and cavities and what's going on inside those, and whether the cavity barriers have been put in place that are expected, and also substitution of materials, where a particular material has been specified by the fire engineer and then the the contractor on site finds they can get something cheaper around the corner and uses it, and instead completely failing to miss the point. I mean, do you have similar issues in Sweden, and if so, how do you deal with them?
I think it's unfortunately also the case. There are cases where, let's say, the whole process or the building process, and we're looking to that also together with one of our PhD students in let's say, the quality process from zero to the end, and also after it's the life cycle system, how it's used. And we do have these problems on they maybe changed materials in the process. In Sweden, it's the building owner who is the final responsibility, and he defines also a bit within, of course, the legal system what the quality control would be, and there's a difference. So it's the fire brigade, for instance, has just a recommendation, and that's at a rather low recommendation level. It's only when it's an operation that the fire brigade suddenly can say, okay, now there's a big problem here, but not in the building phase, and that's different in different countries. I'm aware of that. The biggest problem we have is also renovation. How is the law taking that? Do you take, when you have a building from the 70s and you renovate it, will the building regulations from the 70s still hold for that building, or the new ones? And there's a grey zone in it. And I think this is a challenge, maybe not always research, but it's interesting to see in research what one of the PhD students I have now going to do in this quality, where are the uncertainties maybe.
So we'll add that to your challenges then.
Yeah. Yeah, it wasn't
not exhaustive enough. Yes, okay. Certainly.
So you have performance-based design. So I agree with everything you say. Once there's no implication, she said pointedly, that performance-based design and prescriptive design have different levels of requirements. So if performance-based design and fire engineering, when it's said as if it's about performance only, is deleted from all the talks, and we're speaking properly about the fire safety engineering profession,
exactly.
This applies to everything we do. It's got nothing to do with something being performance-based.
Yeah, I agree. It's a process which is also in the prescriptive, because the underlying of course the regulation in Sweden, that you have the performance-based criteria, and then you have the prescriptive, so-called.
But a prescriptive building envelope is safer than a performance-based building envelope.
Exactly.
Sorry.
Okay.
We'll argue later.
We're cutting back on with engineering. If we trim back on some of the safety margins that are inherent into the prescriptive, sometimes we do, sometimes we don't. But
it's a double. We can.
I'm going to let you guys argue about this later. I'd actually kind of like to weigh in myself.